This lesson is going to be on molar enthalpy. So we introduced what enthalpies were and changes of enthalpies, and actually using specific heat capacity actually calculate actual heat problems. So we're going to kind of continue on the concepts that were kind of discussed at the end of the last video. Now, for thermochemical equations, we represent the moles, and we will actually use half symbols as well, right? Because when we're dealing with the actual enthalpy change, notice that the units are in kilojoules per mole. So what we want is, we want just 1 mole. And we know that if we end up having double the amount of moles in our reaction, we're going to need double the amount of heat to allow this reaction to take place. So we'll always try to simplify equations further to try to achieve the 1 mole, but sometimes you're not going to be able to, or sometimes you're going to have to use the new number of moles, right? Because you might be given a mass, and you'll see what I'm talking about with some of the sample problems we're going to work on in this lesson. Now, for this combustion reaction, we have 1 mole of hydrogen reacting with half a mole of oxygen to produce 1 mole of water, and in the end we are going to be releasing 241.8 kilojoules of energy, or of heat. So again, we're looking at an exothermic reaction, as we said, right? If we find our energy units over on the product side of our equation, we know that energy is being released into the surroundings. Now, the enthalpy change per mole of a substance undergoing a change is called the molar enthalpy and is represented by the symbol delta H and X. Well, X should be a subscript, where X indicates the actual type of change that occurs. So what we have here is we've got a change in enthalpy based on a combustion reaction. So this X is going to say something along the lines of combustion. Okay, so here we have, and it should be a capital H. So we've got H and COMB to represent combustion, right? And notice here it's a minus 241.8 kilojoules per mole, because we're not going to write it down in here. It's really, we're adding the fact that there's energy into this equation. But when we write this out, when we write this change in enthalpy, because this is exothermic, right, and we're just isolating it and asking, what is the amount of energy? What is this change in enthalpy? We put in this negative 241.8 kilojoules per mole. Now, changes in matter may be either endothermic or exothermic, right? So energy put in to the system, energy escaping to the surroundings. So enthalpy changes that are negative, right, as we just saw, represent exothermic reactions, and any enthalpy changes that are positive represent endothermic reactions. So positive enthalpy changes mean energy is input into the system. Now, let's look at some molar enthalpies of reaction. So here's that delta HX that we said, the change in enthalpy with the little x and all that. Little x just represents is what type of enthalpy change is occurring. So if you look at this first example, sodium, right, is being thrown into an aqueous solution, and it's breaking apart into its respective ions. Right, so it goes from being a solid to an aqueous solution. So notice it's the type of molar enthalpy is solution. So delta H solution. We just saw combustion reaction again. So we write down combustion. So we want to know is what kind. Right. Here's another one. Type of molar enthalpy being vaporization. Delta H VAP for vaporization. We are converting this from a liquid to a gas. So vaporization. Freezing, FR, right, when we are converting this liquid into a solid. So what is the enthalpy change that will occur here for freezing? Neutralization, we'll talk about that in a future lesson, right? Notice it's really the same equation. The only thing is we've simplified it to achieve 1 mole of sodium hydroxide reacting with half a mole of sulfuric acid. And finally, formation, right? Almost like synthesis, where we are producing one final result. But what is the enthalpy change? So just be aware of what we use for the delta H, the actual molar enthalpy of reaction. So we've got molar enthalpy, right, of whatever this reaction happens to be. The molar enthalpy of a physical change, such as the vaporization of water, which is an endothermic reaction, can be written as follows. So here we have water as a liquid, converting it to a gas. So we are adding heat, obviously, right? We are adding heat to water in order to increase the kinetic energy of the water molecules to break apart and convert into a gas, right? So we know that this is considered endothermic. So the change in potential energy in this system, the molar enthalpy of vaporization, can be written as follows. So remember, as we said, we've got the molar enthalpy, the change in enthalpy, right? And what is it? It's being vaporized, right? It's converting from a liquid to a gas. So it's vaporization, right? Evaporation. But we will designate it as vaporization. And notice it's a positive 40.8 kilojoules. Why? Because it is endothermic. Okay, so notice here it's positive because it is endothermic. Now, molar enthalpy values can be obtained from reference books or provided by your teacher. So how did we know about this right here? Well, maybe you might be calculating it, but you'll have to be given other information, of course. Most of the times, these numbers will be provided for you in some reference book, maybe in the appendix section of your textbook. So they're not values that you have to memorize. So here's an example of what a table of a table of molar enthalpies that might be given to you by your teacher, or they might find in a reference book, where you will have the molar enthalpy here of fusion, and then the molar enthalpy of the same thing for vaporization. All right. So so keep in mind that be careful when you're reading your sample problems and trying to figure out which one to use, and make sure you use it accordingly. So keep in mind that if we had double the amount of ice, we would require double the amount of energy to melt that ice. So if we had 2 moles, right? Remember, this molar value, right? This is really 40.8 kilojoules per mole that is required, right? Now, if we had double this amount, we would need double this amount in order to change that, double the amount of that liquid into the gas. So to calculate an enthalpy change, delta H, for some amount of substance other than a mole, you need to obtain the molar enthalpy value from the reference source and then use the formula where delta H is equal to N multiplied by your delta HX. So now notice here, this N value, right, is really the number of moles that you're using, right? So the number of moles might be as follows: 2 moles, right? Maybe I might have a 3 here, so here we'd have 3 moles. So in here we would put in 3 multiplied by whatever this molar enthalpy of vaporization would be, right? Now sometimes you might just be given the mass, right? In which, going back to stoichiometry, where you're going to need the molar mass of a substance in order to be able to find your N value. So keep that in mind as well. Sample problem. A common refrigerant, Freon 12, with a molar mass of 120.91 grams per mole, is alternately vaporized in tubes inside a refrigerator, absorbing heat. and condensed in tubes outside the refrigerator, releasing heat. This results in energy being transferred from the inside to the outside of the refrigerator. The molar enthalpy of vaporization for the refrigerant is 34.99 kilojoules per mole. Now, if 500 grams of the refrigerant is vaporized, what is the expected enthalpy change, or delta H? So, what information do we have in this question? Well, we know we've got here a molar mass, which we'll definitely have to use. We've got here this 34.99 kilojoules, which is our enthalpy change, right? This is our enthalpy change of vaporization, right? So our delta H of vaporization. And now the only thing is we're only referring to 500 grams of this refrigerant, right? So this is our mass. So we've got our mass, we've got our molar mass, we've got this of the vaporization, but remember this here, and let me just write out our givens, this here, this 34.99 kilojoules per mole, we're only referring to 1 mole. Okay, 1 mole of this refrigerant. So what we need to do is, we are being given 500 grams with this. So what we're going to do is, now if you look back at your stoichiometry, and we used molar mass, and number of moles, right? So to find the number of moles, right, we cover up number of moles, and we notice that our mass is on top of our molar mass. So to find moles, we divide mass by molar mass. So our mass is 500 grams. We're going to divide it by our molar mass, which was given 120.91 grams per mole. So what we're going to do here is grams are going to cancel out, and when we divide these two together, we're going to get a number of moles as follows: 4.35 moles. So we're not using, right, to vaporize it, we're not using 34.99 kilojoules per mole. We actually need to use this now in conjunction with this new equation. I'm going to use a different color here to show that. So we're trying to find the enthalpy change, but we're using n number of moles multiplied by the enthalpy change, or the enthalpy of vaporization, right? So our n moles is 4.35 moles. We're multiplying it by the enthalpy of vaporization, molar enthalpy of vaporization. So it's 34.99 kilojoules per mole. Now notice the what do you call it? Notice the units and what cancel out, right? Moles cancel out, and all we're left with is kilojoules. So when we divide those together, we get a delta H that is equal to 144.7 kilojoules. So the least number of significant digits is 4, so we also want to make sure that our answer has 4 significant digits. So therefore, the enthalpy change of the refrigerant when it undergoes the vaporization is 144.7 kilojoules. So because the refrigerant vaporizes by absorbing the heat, right, this is going to be positive, right? So it's endothermic. So the freon is going to be absorbing this amount of heat with 500 grams of the Freon 12. Sample problem. What amount of ethylene glycol would vaporize while absorbing 200.0 kilojoules of heat? So the only information that we're given here directly is the 200 kilojoules of heat. That's our delta H. However, right, so this is the amount of energy that it's absorbing. So because it's absorbing, it is considered endothermic. No, so we want to find out the amount of the ethylene glycol. So really, here, we need to find out what the molar enthalpy is of this vaporization of this, right? 58.8 kilojoules for every 1 mole, right? But we are going to be requiring this amount of energy that it's going to absorb, right? So we know that if we compare these two, right, the amount of heat, right, the amount of heat that we're absorbing is greater than the actual molar enthalpy of its vaporization. So we know we're using more than just 1 mole, right? So we want to find out how many moles are we really using. So here's our equation. Delta H is equal to number of moles multiplied by the molar enthalpy of vaporization, right? And this can differ depending on, are you using combustion? Are you using freezing? Are you using fusion? So this part, are you using neutralization? These subscripts can change at any time, but this equation is exactly the same. Now, we want to isolate for N, so we want to get rid of this delta H of vaporization. So the function that we're doing between these two is multiplication. So to get rid of it, we're going to divide it. I'm sorry for the basic little math lesson here, but to get rid of this delta H of vaporization, isolate for our N. We can do it at the end, but I like to move around the letters of the equation earlier. So what we do on this side, we got to do on this side, delta H of vaporization. So what happens, this cancels out, leaving us with just our N value. So what we're left with is N equals delta H over delta H of vaporization. So all we do now, substitute our numbers in here. So instead of delta H, we put 200 kilojoules. Don't worry about the 0.0 for now. Just remember that at the end when you're dividing, your final answer has to have the right number of significant digits. Significant digits in our question, only 4 of them, so our final answer should also have 4 significant digits. 58.8 kilojoules per mole. Right, this is a number I introduced, so I usually do not use this for significant digits because it's a number that I introduce into the question. It's not part of the question directly. If I wrote it in the question, then we would use it, but because I did not write it specifically in this question, we're not going to use 3 significant digits for our final answer. Anyhow, kilojoules divide out, and all we're left with is moles. So our N value, when we divide them, equals 3.401 moles. So therefore, the amount of ethylene glycol that would vaporize when we are when it's absorbing this amount of heat is 3.401 moles of ethylene glycol. Calorimetry of physical changes. Studying energy changes requires an isolated system, one in which neither matter nor energy can move in or out. Okay, so we can use 2 polystyrene cups. I talked about this in a previous video. Pretty much you just get 1 cup as follows. You kind of cover it up with another one, and you've got your thermometer through it, right? And in here pretty much you would have whatever your solution is, and especially if you're doing a physical change, you're just changing states, most likely, you know, from a solid to liquid, liquid to a gas, gas down to a solid, right? So in order to take these kind of measurements, so that's what we'll use as a nice, simple, very effective calorimeter. Now, when we investigate energy changes, we base our analysis on the law of the conservation of energy. The total energy of the chemical system is equal to the total energy change of the surroundings. So here what we have is the system, right, the delta H of our system, and the Q value, the heat value of the surroundings. Okay, so now pretty much what we're going to be looking at really between such examples is really when doing with some of these physical changes, one of the physical changes is dissolving, right? So what happens is when we're dissolving, we are dissolving the solute, and the surroundings would be our solvent. Okay, so what you'd be doing is, odds are, a lot of the times the solvent will be water, right? So if a solvent is going to be water, we're going to find our Q is equal to MC delta T, as we've seen in the previous sample problem. Okay, and our delta H of the system is pretty much maybe whatever might be doing the dissolving, as just an example of a physical change. Now, these are three assumptions often used in calorimetry. No heat is transferred between the calorimeter and the outside environment, so everything kind of stays within the calorimeter. Any heat absorbed or released by the calorimeter materials, such as the container, is negligible. So if for some reason the container is giving off any heat, really we don't really treat it, right? Keep in mind that a dilute aqueous solution is assumed to have a density of the following: 1 gram per milliliter. And when we're looking at the specific heat capacity, or Q value, for water, we're going to be referencing 4.18 joules per gram degrees Celsius. Notice here 4.18, but it's in kilojoules per kilogram. We made the conversions. Remember, for every 1 joule, there's 1,000 kilograms. For every 1 kilojoule is 1,000 joules. But for every 1 gram, for every 1 kilogram, we have 1,000 grams, right? So obviously this isn't going to make any difference, but just be careful of the units. So if you're wondering why we got this, well, remember, our joules and grams went to about 1,000, right, in order to convert it to kilojoules and kilograms, so it stayed exactly the same, right, because our top number and bottom number are exactly the same number. Let's look at the enthalpy change between an exothermic versus an endothermic reaction. In an exothermic reaction, pretty much we are going to have our reactants that are going to have a high potential energy. So we're going to have a high potential energy for our reactants, and then our products are going to have a low potential energy. So these are the products. So what we're going to do, what's going to happen in an exothermic reaction, we are going to have this drop in potential energy, right, as pretty much heat is being released, right? So heat is being released. Exothermic means heat being released. So what we're going to do is we're going to have this delta H and a drop in the delta H. So therefore, this change in enthalpy for whatever the reaction is going to give us a negative value, right? So, in other words, temperature is going to increase in exothermic reaction. So if we're looking at the equation Q is equal to MC delta T, if this delta T is the only way to get a negative value for our Q, right? So what's going to happen is this value, to get, right, let's say to become positive, will have a higher final temperature, which will be greater than, of course, the initial temperature, which will give us a positive Q value. But in terms of our Q value is equal to our change in enthalpy of whatever the reaction is. So to get a negative value, we're going to have a positive Q in terms of a specific heat capacity question, right? So a delta H of the reaction will give us a negative value, right? So what's going to happen is we're going to have an increase in temperature. So the minute we see an increase in temperature, we know it's going to be exothermic. So if it's exothermic, right, we are going to have energy that is pretty much being, heat that is actually being released. Now let's look at this endothermic reaction. And in this endothermic reaction, our reactants will have a low potential energy, And our products, on the other hand, are going to have a high potential energy. So all of a sudden, this change in enthalpy is going to be a positive value because the energy is being absorbed by within this reaction, right? So what's going to happen, how can you tell if the enthalpy change is going to give us a positive value? Well, our enthalpy change will result in a temperature being decreasing, right? So the initial temperature is going to be higher than the final temperature, and as a result, we're going to get a positive value for our delta H. So what we're going to have is a positive delta H of a reaction is going to result in a negative Q value, right? So in other words, why is this negative Q? So let's go back to explaining this equation here. Negative H of the reaction is equal to a positive Q. Positive delta H of the reaction is equal to a negative Q. So in terms of an exothermic reaction, well, where is the energy that is coming into this system, right? Because in other words, this represents the system. This here is going to represent the surroundings. So the surroundings is giving up heat to the which will result in this change in enthalpy. It's the surroundings is giving in the heat to the system, and that system is absorbing that reaction. While on the other hand, here with this negative delta H reaction for an exothermic reaction, the Q is positive, right? So what's happening pretty much is the other way around. Now the system, right? And here's the surroundings. The system is giving up heat to the surroundings, hence the negative value, right? It's a negative value because it's giving up that heat, right? Q here is negative, so it's giving up the heat to and that's where it's coming from. So in terms of these enthalpy changes, right, for an exothermic and an endothermic reaction, it's either going to be the system giving the heat to the surroundings or releasing the heat to the surroundings, or it's going to be the surroundings giving up the heat to the system, but it's the system that is going to be absorbing that heat, hence the name endothermic. And we'll understand this a little bit better with the sample problem. Let's look at this sample problem here. In a calorimetry experiment, 7.46 grams of potassium chloride is dissolved in 100.0 milliliters of water, which is equivalent to 100 grams, at an initial temperature of 24.1 degrees Celsius. Now, the final temperature of the solution is 20 degrees Celsius. What is the molar enthalpy of solution of potassium chloride? So let's go back and let's look at some of the information that we're given here. We're given the mass of the potassium chloride, which is 7.46 grams. We're given here the volume, right? But more importantly here, we're going to be given the mass now of the water. So this is pretty much the surroundings, right? We've got an initial temperature, so Ti being 24.1 degrees Celsius, and the final temperature, Tf, being 20 degrees Celsius. What is the molar enthalpy of the solution? Well, another thing that's really important to be able to address in this question is really potassium chloride. This is, so we've got the potassium chloride in this experiment. It is dissolved, so it's dissolved in water, right? So what's happening here is pretty much the KCl is going to dissolve, right? While the water, which is really the surroundings, right? So in terms of this reaction would have a change in delta H, or enthalpy change, based on a solution reaction, right? Now, a few things to also know, well, of KCl. We want to find out the molar mass of KCl, right? And the molar mass of KCl is 74.6 grams per mole. So what we're going to do is we're going to try to find out the number of moles, because what's happening here in this reaction, we have a change in enthalpy of this dissolving of the potassium, right? And outside, right, of this, we've got really the heat of the water, so the calorimeter, right? So delta H is going to represent the potassium dissolving. The Q here is going to represent the water. Now, however, this delta H we know is equivalent to delta H is equal to N times delta H of whatever the reaction is, which happens to be a solution. So what we need to do is we need to be able to find this molar enthalpy of this actual solution, right? So in order to find really this is what we're going to get. So what we're going to do is we're going to substitute this here into this equation, right? Because we can actually find N using here mass and the molar mass, right? So think stoichiometry, you know, and trying to calculate the number of moles. So to do that, well, if we divide these actual two values, mass divided, we are going to get a value of moles, which is 0.1 moles of KCl. Okay. So now we've got, instead of delta H, we're going to put in N delta H of solution is equal to Q. But what does Q represent? Q is represented by MC delta T. So this is going to represent pretty much the heat transfer from the water, if there is one. And here we've got pretty much our change in enthalpy of the potassium chloride dissolving. Now, one thing to keep in mind, notice here this change in temperature. We've got TF is equal to 20 degrees Celsius. And just for argument's sake, I'm going to remove the 0.0 just when I'm solving this question. And we've got an initial temperature of 24.1 degrees Celsius. So in other words, our delta T is going to equal to 20 subtracted by 24.1 degrees Celsius, which is going to give us a value of negative 4.1 degrees Celsius. So now, because we get this delta T being a negative, we know that energy is going to, or heat is going to leave from the water to cause this KCl to dissolve, right? So in other words, because this value is a negative 4.1 and we're dealing with our pretty much our delta H is equal to Q, right? So our solution and pretty much outside of our solution, right, our surroundings, we are looking at pretty much what we call an endothermic reaction. So what's happening is this Q value that we're going to get on this side is going to give us a negative value. So if we've got a negative value, it means heat is leaving from this system of the water going to, you know, dissolve this KCl. So what we're going to do here now is let's start to substitute our values into this this question. So let's do the following. So what we're going to do is we're going to get rid of N here, right? So what we're going to do is get rid of N, divide this side by N, divide this side, and let's erase some of this here, and divide this also by N, right? So the N's divide out, which will leave us delta H of solution is equal to mass times specific heat capacity of water times the change our numbers. So the mass of the water, we got 100 grams. We're going to multiply that by the specific heat capacity of water, which is 4.18 joules per gram degrees Celsius. And we're going to multiply it by negative 4.1 degrees Celsius. We're going to divide this by the number of moles that we got of the potassium chloride, which is 0.1 moles. And now what we're going to do is go into canceling out our units, or dividing out our units. Grams divide out, degrees Celsius divide out, and all we're left with is joules per mole, which are the units for our enthalpy change, or our molar enthalpy change. So when we divide these two, we are going to get a delta H of solution, which is going to give us a Q value here that is negative. All right, so now be careful with this. We're going to get negative 17,138 joules per mole. However, this is the energy that is being released by the water. So when we're looking at our change in enthalpy, it will be the opposite. Because remember, we've already determined that it's endothermic. And if it's endothermic, delta H, right, of whatever the reaction is, which happens to be a solution here, has to be a positive value. So in other words, all we're going to do is drop this negative value. Right, we're going to drop this negative value because our delta H of the solution has to be positive if it's going to be endothermic. And how do we know that it's endothermic? As we said, the change in water is going from a high temperature to a lower temperature. So for water to decrease in temperature, the energy that is required here to drop this temperature goes somewhere else. Where does it go? It actually goes to dissolve the potassium chloride. Hence the reason why this value now, based on three significant digits, because 3 significant digits is the least number of significant digits in my question, is equal to 17,100 joules per mole. And more specifically, I could convert this to 17.1 kilojoules per mole of energy. So, in other words, pretty much, enthalpy change for this, right, that dissolves the potassium chloride is 17.1 kilojoules per mole. Now, the reaction, as we said, is endothermic. The molar enthalpy of the solution for potassium chloride has to be in a positive value, right? Because really energy is being released from the water, right, Q, to dissolve the potassium chloride. Sample problem. What mass of lithium chloride must have dissolved if the temperature of 200 grams of water increased by 6 degrees Celsius? The molar enthalpy of the solution of the lithium chloride is minus 37 kilojoules per mole. Now, thing with this question, right, and as we talked about before, was that we had delta H of whatever the reaction is, right, is equal to Q, right? So whatever the reaction is, and pretty much our surroundings, right? So in this reaction, we've got lithium chloride, right? So now this lithium chloride value, right, this delta H, we are getting to be a minus 37 kilojoules per mole, which means this Q value, because this side, if this side is negative, this side is going to be positive, right? So if this side is negative, right, that means this reaction, right, this temperature, notice this temperature, the temperature of the surroundings of the water of this increased, right? So if the temperature increased, that means we know we have an exothermic reaction. So let's actually work this this question out. So here's a list of some of the important information that we actually have. We've got a mass of 200 grams of water. We've got a delta T of 6 degrees Celsius, which is increased. We've got a delta H of the solution to be 37 kilojoules per mole, right? We've got a C value, which is 4.8, and notice it's kilojoules per kilogram degrees Celsius, which means we are going to have to convert this to kilograms, which will be equal to 0.2 kilograms. And the reason why we do this is, look at the units here of the delta H that's given. It's given to us in kilojoules. So we're going to want to make sure that our C value is going to be in kilojoules, but also change to keep kilojoules per kilogram, so you're not really changing, because odds are the values that you're given are going to be in joules per gram degrees Celsius. However, to convert joules to kilojoules, there are 1,000 joules. Right? Now, to convert grams to kilograms, there are 1,000 grams. So in other words, 1 to 1, as we have here, or 1,000 to 1,000 is still 1 to 1. So all you have to do is just make sure that you're changing the units to kilojoules and kilograms instead of joules and grams, right? So all you're doing is, if your units are joules per gram, just add K to both of these if your delta H is in kilojoules per mole. Right? So we've got a molar mass of lithium chloride being 42.4 grams per mole, and we can actually find the actual mass of the lithium chloride. Now, as we've said before, right, our delta H, right, of reaction is equal to our Q value, right? So our delta H pretty much is as N delta H of solution, right? And it's a solution. Why? Because lithium chloride is dissolving in water, right? Our value here of Q, right, which is MC delta T. So here we have now our N value. We can actually find the number of moles. And that's actually really what we're trying to find. We're trying to find the number of moles. So what we're going to do is we're going to get rid of this delta H of solution. So to do that, we're going to divide this side by delta H of the solution, divide this side by delta H of solution. So now those divide out, and all we're left with is N is equal to MC delta T over delta H. So let's substitute our numbers. Now the mass here is the mass of the water, right? Because this is part of our Q. So our mass of the water, 0.2 kilograms. Our C value, as we said, the specific heat capacity of water, 4.18 kilojoules per kilogram degrees Celsius. Our change in temperature, as we said, is 6 degrees Celsius. And we're going to divide this by a negative 37, negative, let me delete part of this. So negative 37 kilojoules per mole. Now, a few things to keep in mind. Well, I like to include my units. Why? Because I use my units to figure out what the units will be of my final answer. Now, because we are trying to find the value of N, which is the number of moles, we cannot have a negative value. And if we continue with this question as is, our answer is going to give us a negative value. And in fact, we do not have a negative value. We cannot have a negative mole value. So what we're going to do is we're going to ignore this. But remember, because this delta H of solution was 37 kilojoules per mole, right? This told us that we had an exothermic reaction, which means that energy or heat was released by the lithium chloride to the water. As a result of lithium chloride releasing heat, it released heat where? To the water. What happened to the water? It increased temperature. By how much? 6 degrees Celsius. So anyhow, let's go back to this question. So when we multiply all this out, we get a value. And I'm going to round it off. I'm going to do something I shouldn't be doing. And we're going to get a value of 0.14, which really should be actually, I'm not going to do it. Actually, I won't reduce it. So I'm going to get this value, 0.135567567 moles. So this is my N value. This is the number of moles that I'm going to have of lithium chloride based on this mass. So what I'm going to do now, I've got the number of moles, I've got the mass, the molar mass, sorry, of lithium chloride, which is 42.4 degrees Celsius. So what I'm going to do is I'm going to take this value here, I'm going to multiply it by 42.4 grams per mole. Again, keeping the units, moles divide out, all I'm left with are grams. So the mass of the lithium chloride is equal to 5.74806 dot dot dot, keeps going, right? Grams. But least number of significant digits in my question are 2. So this 5.7 are my 2 decimal significant digits. So the mass is equal to 5.7 grams. So in other words, the mass of the lithium chloride that's required to raise this temperature of the water by 6 degrees Celsius when it dissolves in the water, right, is going to be 5.7 grams. Now, finally, calorimetry of chemical changes. So what we've looked at, all the sample problems that we've looked at, have dealt with physical changes. But now, the assumptions and formulas applied are identical to those used in the analysis of energy changes during state changes and dissolving, right? So these right here, right, represent physical changes. But whatever we've done, any assumptions that we've made, any of the formulas that we've used is exactly the same when dealing with chemical changes. Okay, so aqueous solutions of acids and bases react in the form of a neutralization reaction, and keep in mind that the molar enthalpy deals with really the heat of neutralization or the enthalpy of neutralization. So the delta H and the X will be of neutralization. And we will see this in a future lesson.